the universe continues to expand, revealing more of its mysterious and awe-inspiring nature. In 1929, scientists discover the expansion of the cosmos, a revelation that transformed our understanding of the universe's evolution. As our knowledge deepened, we realized something even more profound. Our very bodies are composed of elements forged in the hearts of ancient stars. By 1957, it became clear that the night sky, far from being a mere visual wonder, is a reflection of the staggering forces that govern the cosmos. The universe is constantly in motion, teeming with activity and mystery, much of which remains beyond our comprehension. We are left to wonder about our place in this immense system, why we exist, how planets and stars came to be, and what other possible outcomes the cosmos might have entertained. Yet, human nature often leads us to overlook cosmic phenomena until they become pressing or potentially dangerous. Such example is Betelgeuse, a massive star in the constellation Orion that has recently begun to show signs of instability, trembling in a way that suggests something significant and potentially ominous may be unfolding. Betelgeuse is not just another star. It is a red supergiant, a colossal celestial body whose sheer size dwarfs that of our Sun, making our star appear minuscule by comparison. Located over 640 light-years from Earth, Betelgeuse's apparent brightness in our night sky belies its true distance. In cosmic terms, 640 light-years is a vast expanse. Even traveling at the speed of light, it would take more than 6 centuries to reach it. An impossible journey with today's technology. Realistically, it would take over 12 million years to travel that distance, using conventional spacecraft, the span of time far exceeding the entirety of human history. This puts into perspective the extraordinary magnitude and power of this distant star, which has been exhibiting intense trembling and instability for some time. But stars appear serene from Earth. They are anything but calm. Regardless of their size, stars are dynamic systems governed by complex physical processes. Scientists have long studied Betelgeuse. Due to its pulsating nature, it has been known as a variable red supergiant, meaning its brightness fluctuates over. These pulsations are driven by the star's internal mechanisms, causing its luminosity to vary in cycles that range from tens to thousands of days depending on whether it is expanding or contracting. These variations make Betelgeuse an object of intense interest, particularly since its changes in brightness are unusually pronounced. Its magnitude has been observed to fluctuate between 0 and 5, a remarkable range that reflects the volatile nature of the star. Betelgeuse's brightness variations follow specific cycles. The shorter cycle lasts approximately 185 days, while the longest spans over 2,300. These cycles can be measured with great precision and have offered astronomers critical insights into the inner workings of the star. In February 2021, the star's band brightness dropped to 1.1614, one of the lowest levels recorded in years, an anomaly that deviated sharply from its historical pattern. This drop triggered concern and further observation as it hinted at deeper changes occurring within the star. Betelgeuse's striking red hue adds to its intrigue. This color results from a relatively low surface temperature of around 3,500 Kelvin, significantly cooler than the Sun's surface temperature of approximately 5,500 Kelvin. Despite its massive size, this lower temperature means Betelgeuse emits less energy per unit area than our Sun, which paradoxically makes it appear less luminous in certain contexts, but makes the current situation more Alarming is the fact that Betelgeuse, while typically stable for a red supergiant, has recently transitioned into a more volatile phase. The shift is believed to be tied to changes in its core. As with all stars, the fusion of hydrogen into helium fuels Betelgeuse energy output. However, in red supergiants nearing the end of their lives, the hydrogen in the core becomes depleted. This depletion causes the star's outer layers to expand as the core contracts, leading to increased instability. During this stage, helium begins to accumulate around the core, initiating a new fusion process known as helium shell burning. In this phase, helium atoms fuse to form heavier elements such as carbon and oxygen, releasing bursts of energy that counteract gravitational collapse. Unlike hydrogen fusion, which occurs more steadily, helium fusion is erratic. This irregularity causes bursts of energy to build up and release impulses, disrupting the star structure and creating powerful stellar winds. The winds expel vast amounts of material from the star's outer layers, a process that further alters the star's internal balance. As a result, Betelgeuse's outer shell undergoes continuous expansion and contraction, a rhythmic phenomenon we observe from Earth as changes in brightness. This pulsating behavior is akin to a cosmic heartbeat, revealing the turbulent life hidden beneath the star's surface. To understand these phenomena more deeply, astronomers rely on two key observational techniques: photometry and spectroscopy. Photometry involves measuring the star's light output over time, which reveals patterns in its brightness and helps track the pulsations of stars like Betelgeuse. These light curves provide a direct window into the star's behavior, making it possible to detect changes that may not be immediately visible to the naked eye. Spectroscopy, on the other hand, analyzes the light emitted by the star across different wavelengths. This method uncovers details about the star's temperature, composition, and motion. Betelgeuse pulsates, its spectral lines shift, revealing crucial information about the internal processes driving those pulsations. By combining data from photometry and spectroscopy, scientists can construct detailed models of stellar behavior. These models use the laws of physics, including equations governing fluid dynamics, thermodynamics, and nuclear fusion, to simulate the inner workings of stars. Using powerful computers, astrophysicists can test how various internal conditions affect a star's pulsations and predict future changes in its structure and luminosity. These simulations bridge the gap between theory and observation, allowing researchers to test hypotheses against real data gathered from telescopes. Especially fascinating process within Betelgeuse is stellar convection. Energy is produced in the core through fusion. It moves outward toward the star's surface. In red supergiants, this energy transport occurs through convective currents. Hot plasma rises from the interior toward the surface, while cooler material sinks back down, forming a churning dynamic system that transfers energy through motion. The convection currents cause fluctuations in the energy reaching the star's outer layers, affecting its brightness. More energy reaches the surface, the star appears brighter. When less energy arrives, it dims. This dynamic transport of energy contributes significantly to the pulsating nature of Betelgeuse. The pulsations are not mere random fluctuations but often follow discernible patterns, especially in variable stars like Betelgeuse. The cycles of brightness are intricately linked to the expansion and contraction of the star's outer envelope. As the star expands, its surface area increases, causing the outer layers to cool and darken. As Betelgeuse approaches the final stages of its stellar life, these pulsations and convective processes become more pronounced. The depletion of its nuclear fuel will eventually culminate in a supernova, a cataclysmic explosion that marks the death of a massive star. While such an event is likely thousands or tens of thousands of years away, the signs of its approach can be detected in the star's behavior today. For now, astronomers continue to monitor Betelgeuse's pulsations, brightness variations, and energy emissions, piecing together clues about the complex forces operating within the celestial giant. Each fluctuation in light, each spectral shift adds to our understanding of how massive stars live, evolve, and ultimately die, enriching our view of the universe and our place within it. These continued investigations into Betelgeuse do more than simply tell us about a single star. They help us decipher the life cycles of all massive stars. Betelgeuse acts as a kind of natural laboratory, allowing astronomers to test their theories about how stars behave during the late stages of their evolution. Massive stars like Betelgeuse live fast and die young by cosmic standards, while our Sun is expected to live for over 10 billion years. Betelgeuse has likely existed for only around 10 million years. Yet, its mass, estimated to be between 10 and 20 times that of the Sun, has propelled it rapidly through its life stages. This accelerated timeline means that Betelgeuse is now nearing the end of its life, preparing to explode as a supernova, an event that will scatter the elements created in its core across the cosmos. These elements, oxygen, carbon, iron, and many others, are the very building blocks of life. In a real sense, we owe our existence to the death throes of massive stars that exploded long before our planet ever formed. The irregular dimming that Betelgeuse experienced in late 2019 and early 2020, which became known as the Great Dimming, puzzled scientists and captured public attention. During this period, Betelgeuse's brightness dropped more dramatically and suddenly than ever observed before, reaching its lowest visible magnitude in over a century. Initially, some speculated that this might be a precursor to an imminent supernova, but further analysis revealed a different explanation. Observations from space telescopes, including the Hubble Space Telescope, suggested that the dimming was caused by a large cloud of dust ejected from the star's outer layers. The dust formed when a portion of the star's surface cooled suddenly and expelled material into space, which then condensed into dust and partially obscured the star's light from our perspective on Earth. This event demonstrated the powerful forces at work within red supergiants. The outer layers of these stars are not stable but can be pushed away by strong stellar winds or eruptive events caused by convection and pulsation. In the case of Betelgeuse, it seems that a massive convective cell rose to the surface, cooled, and released a burst of plasma. As this material cooled further, formed a dense cloud of dust that temporarily blocked the star's light. This kind of behavior is consistent with the idea that Betelgeuse is undergoing increasingly unstable changes as it approaches the end of its life. For astronomers, such events provide a rare and valuable chance to observe in real time the processes that precede a supernova explosion. Despite the dramatic dimming, Betelgeuse eventually returned to its usual brightness, reinforcing the idea that the star still has some time before it meets its explosive end. Nonetheless, the episode served as a vivid reminder that stars are not static points of light, but complex dynamic systems governed by the interplay of nuclear fusion, gravity, and radiation. The outer envelopes of stars like Betelgeuse are essentially in a constant state of flux, responding to changes deep within the core that ripple outward in waves of motion and light. In the case of red supergiants, this instability is particularly pronounced, making them highly variable and sometimes unpredictable. Understanding Betelgeuse also helps scientists predict what will happen to other stars, and ultimately what might happen to our own sun, albeit on a much smaller scale. While the sun is not massive enough to become a supernova, it too will eventually exhaust its hydrogen fuel, expand into a red giant, and shed its outer layers. The study of red supergiants like Betelgeuse offers insights into this process, revealing the physical mechanisms that govern stellar aging and death. The differences in scale are immense, but the underlying principles, fusion, convection, mass loss, are the same. By looking at Betelgeuse, we are looking into our own distant future, magnified in both time and intensity. Another important area research involves modeling Betelgeuse internal structure using data collected through a method called astroseismology. This field studies the oscillations within stars, much like how seismology on Earth uses earthquake waves to learn about the interior of our planet. The stellar oscillations provide clues about the density, composition, and temperature of different layers inside the star. When applied to a pulsating giant like Betelgeuse, astroseismology can help astronomers refine their models and better understand how energy flows through its vast convective layers. These models are essential for making accurate predictions about when and how Betelgeuse